Alright, well, here goes nothing. So you have a test coming up Wednesday, and just wanted to go through some things. So the key concept, of course, being able to convert degrees to radians and vice versa. Key relation, of course, 180 degrees is equal to pi radians. We've done a bunch of those. I might ask you a question about arc length and how to calculate it. Remember the S equals R theta formula. And must use radius, must use radians for that to work out right. You have the area of a sector. Formula for that, 1/2 theta r squared. Not all of you got that on the quiz, so if you didn't, probably should look at it. But this formula makes a lot of sense. If you put in 2 pi radians, you get back pi r squared, which of course is the area of a circle. Now, we also use the unit circle to define cosine and sine, as you may recall. So, that's well and good. Sometimes you might face another kind of problem where I give you sine or cosine and ask you to find the other one, etc. And there, it's important to know Pythagorean identity, the cosine squared plus sine squared equal to 1, and equally important to know that you can solve that to get cosine in terms of sine or sine in terms of cosine. But you got to beware the plus or minus. You got to choose the plus or minus as appropriate to the quadrant, right? Remember how it goes. How's it go? How's it go? If I can draw. So cosine and sine, they're both positive up here. Cosine's positive here. Sine's negative here. Cosine's negative here. Sine is positive here. They're both negative down here in quadrant 3. So we're looking at quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? And then of course you have the coordinate axes in between those. Alright. And I believe your book has a special name for the angles of 0, pi over 2, pi, 3 pi over 2. Don't ask me what it is right offhand. I read it. I don't remember it. My apologies. Now, you should know your trigonometric ratios, right? You got to know sine, cosine, tangent for the triangle. Remember, it's got to be a right triangle. If it's not a right triangle, then other things come into play. We'll get to those before too long. We're not quite there yet. So right triangle, you have the angle, you have the side adjacent to the angle, the side opposite to the angle, of course the ever special hypotenuse, and so you can define your acute angle, right triangle, trigonometric ratios, cosine, adjacent over hypotenuse, sine, opposite over hypotenuse, tangent, opposite over adjacent, secant, the ratio 1 over cosine, cosecant's 1 over sine, cotangent's 1 over tangent. And I would expect I'd ask you questions based on all this stuff, right? I also talked about coterminal angles, reference angle, remember? And I also just had to picture angles in each quadrant, right? So try to come up with a couple more examples here for today for you. I have written the test, so let's see here what I got. Uh-oh. My phone is buzzing. Oh, it's going to have to wait. Alright, so let's start out with a degree conversion problem. Example. I'll work my pen, come on. Fine, don't work. You're dead to me. Ha! I have markers. Example. If theta equals to 2 pi over 3 radians, then find the angle in degrees. Alright, here's how it goes. So remember, pi radians equals to 180 degrees. So theta equal to 2 pi over 3 radians equals to, let's see, pi radians. So we got 2/3. Pi radians is 180 degrees, right? And so that is 2 times 180. I probably should have got my calculator. 360, I think that's 120 degrees. Yeah, that makes sense. So 120 degrees it is. So if you think about it, 3 times 120 degrees is 360 degrees. 3 times 2 pi over 3 radians is 2 pi radians. That makes sense, that we multiply both to get a full cycle. Alright, so that's just a check on my answer. So there's an example. Next example. Example 2. Alright, let's find an angle 0 less than, let's say, alpha plus 360 degrees, which is coterminal to theta equal to, let's say, minus 260 degrees. Alright, so there's my example 2. So I'll draw a picture of this as best as I can. Best as I can. So minus 260, right? So start out here and kind of go clockwise. That'd be minus 180, and that would have been minus, it's basically all the way up to here almost. See, because it's minus 80 degrees. So basically the reference angle, this is the reference angle, this isn't the reference angle, the reference angle to this right here, I'll make it green. The reference angle is 80 degrees. See that? That's the theta prime. Now, I didn't ask about that in example 2, I'm just saying that's the reference angle. Now, so I'm supposed to find an angle coterminal, right? Coterminal there. between 0 and 360 to this minus 260. So the game we play is to add or subtract multiples of 360 until you fit in there, right? So check it out. If we do minus 260 plus 360, that gives us a coterminal angle, and that of course gives me 100 degrees. So the answer is alpha equal to 100 degrees, which makes good sense because I told you theta prime, oh I didn't tell you, I should have told you theta prime was 80 degrees. So it's like 80 degrees up to here, and it's 100 degrees like that. Right, so 80 plus 100, 180, full sweep like that. So the more you know about how the angles have to add to 180 degrees, like along a line, helpful it is, right? Just like the sum of the angles inside a triangle must be 180, something else to keep in mind. So that high school geometry stuff come back to help you. Alright, let's go on here. I think I got that in frame. So, example 3. Let's convert a degree to a radian. Convert 460 degrees to radians. Alright, remember, key is use your conversion factor. I used the substitution principle the last one we did. This one I'll use a multiplication by 1 idea. So 460 degrees, I'll multiply by 1. So I want to change from degrees to radians. So I'm going to put pi radians up top. And I'm going to put 180 degrees down bottom. This of course is multiplying by 1. And it's also known as a unit conversion factor. Degrees be canceling, and I need to go get my calculator. In a moment. I'm back. Alright, so 460 times pi divided 180 gives me approximately 8.029 radians, which makes sense. 2 pi radians is about 6.28. That's 360, so it should be bigger. Should be bigger than 360 for sure, since it's 460. So there's a good example. Example 4. Example 4. Picture, see, let's picture an angle as well as its reference angle. All right, here we go. Picture both theta equal to, let's say, 250 degrees, as well as its reference angle. Sorry about my handwriting. It's horrible. Alright, here we go. So 250 degrees lies in quadrant 3, I believe, because we sweep 90 and then another 90, that gives me to 180. So 180, 250 minus 180, what's that? How many do I have left to go? 70 degrees left to go. So then I keep swinging down, down, down. Basically like that, right? So there's my direction. Theta equal to 250 degrees. Alright, what's the reference angle then? The reference angle is the acute angle formed sweeping from either the positive or the negative x-axis closest to the direction we're going. In this case, it's the negative x-axis, and it's this angle right here, which we typically denote by theta prime. In this case, it was 70 degrees. So there you go. Reference angle. Remember, reference angles are acute. All right. Let's look at example 5. Alright, so example 5 is a little bit more interesting. So here it comes, just as soon as I get to it. Oh, please. Here we go. So here's the question. Here's the question. Given sine of t equals to 3/5 and the angle is in quadrant 2, find cosine t. Find cosine. Now the problem I had on the quiz, I hope you noticed in my solution I omit I gave you something that was impossible. I told you like cosine was negative where it had to be positive or something like that. Sorry about that. Some of you should have pointed me out on that on the quiz. Not a good sign. But anyway, excuse me. Alright, so the way to go here is to use the Pythagorean identity I talked about at the start. So, what to do is say, okay, so cosine squared t plus sine squared t is 1. We know sine, we're trying to solve for cosine. So cosine t is plus or minus square root 1 minus sine squared t. Alright. And we're in quadrant 2, right? So 2 means we're going to choose a negative cosine. So we've got cosine t is minus square root 1 minus 3 over 5 squared and so that's minus the square root. Oh, I'm supposed to make that an 8. Start with that. 8 sine 3/8. So, alright. And so that gives me 1 minus 9, 8, 64, right? So that's minus the square root 64 minus 9 over 64, which is, what is that? That is 64 minus 9 is, good grief. I don't trust myself doing anything at the moment. 64 minus 9. 55. So we get minus the square root of 55. Square root of 64, of course, is 8. And so there's the exact result right there. Okay. Doesn't have to be complicated. Just remember, you use sine squared plus cosine squared. Choose the sign, plus or minus is appropriate to where you are. Remember it? Alright. Alright. Next one. Next example. Next example. Here we go. Say find the exact, example 6 here. Find exact numerical values exact numerical values for sine theta, cosine theta, tangent theta, secant theta, cosecant theta, cotangent theta, given triangle pictured below. Alright, so triangle, triangle, triangle. Alright, suppose I'll put my theta here. So my right angle, of course, 7, 3. There we go. Alright, so first of all, so that's what's given. That's what's given. I'll make the solution in red. So first of all, probably be nice to know Pythagorean theorem. So up here we got what? Square root of 7 squared plus 3 squared, which is 49. 49 plus 9. 40. Oh, goodness gracious. 49 plus 9. Oh, stop that. 49 plus 9. 58. Square root of 58 is the hypotenuse. Okay. So now, if I understand, we can write down the trigonometric ratios. Simple business. So let's do it. Sine theta, opposite over hypotenuse. And the reciprocal to that, cosecant, is 1 over sine theta, so we have square root of 58 over 3. Cosine theta, we do adjacent, which is 7 over hypotenuse, square root of 58. Then the reciprocal to cosine is the secant theta, and that is the square root of 58 over 7. We have tangent theta, which is adjacent over opposite, I believe. Wait a minute. No, opposite over adjacent. What's wrong with me? Oh, that's right, I've got pneumonia. Trying to make sure I didn't do it wrong before. Yeah, it's supposed to be 3 over 7. 3 over 7. So cotangent, 7 over 3. There you go. That's how you do it. It's not too bad, right? Alright, so another example. Another example. There we go. So here I ask us to find the lengths of the sides of the triangle pictured below, find the opposite side length, find the adjacent side length. And so suppose that's 60. It's not a very good picture of a 60-degree triangle, but oh well. You can forgive me. Suppose this is 60, I'll make this 20. Now the question is to find the opposite side length and the adjacent side length. So how do we do that? Well, we use the trigonometric ratios, right? So I find it's sometimes. Useful to give labels to what we know, rather don't know. A and B, that's what we're trying to figure out, right? And we know that cosine of 60 is equal to A over 20, right? So that tells me that A is 20 times the cosine of 60. And of course I could use a calculator, but that's a special angle. So we know that that's 20 times the square root of 3 over 2. I do intend for you to have that, you know, right triangle special. This deal here, right? So, where are we? Pi over 3 is 60 degrees, right? Oh, I can't do math. Look at that, I made a mistake. It wasn't the square root of 3 over 2, it's cosine of 60. Dummy. Dummy, dummy, dummy. So that's 20 times 1/2. So 10. A equals 10. Now, on the other hand, sine of 60 degrees is opposite B over hypotenuse 20. So that tells me B is 20 times the sine of 60. And the sine of 60 is, as I was saying a second ago, square root of 3 over 2. So that's 10 root 3. So B is 10 root 3. So there you go. Figured out the side lengths, the missing side lengths of the triangle given the angle and the hypotenuse. It's a very standard problem, very important applications of trigonometry, maybe the most important application in this chapter, especially to physics, breaking vectors down into components. So much of what's needed is this. Alright, see if I got another example for us. All right. Well, you're running kind of low on energy here, but I guess I would kind of expect on the test that I have one that's like, you know, graph a sine function carefully for a couple cycles and graph a cosine function carefully for a couple of cycles. I guess I have energy for that. So hopefully you can graph better than I can at the moment. They don't have to be perfect, but you should try to include important features, right? Like, you know, things like that's pi, this is 2 pi, minus pi, minus 2 pi. Of course we're looking at sine theta here. So and this is like pi over 2. You know, the more that you label on it, the better, really, right? And in contrast, cosine, almost the same picture, right? Just wherever there's a maximum, and this for minimum in sine, there's a zero cosine, and vice versa. Oh, it's horrible. I'm sorry, guys. So roughly speaking, that's cosine. Very roughly speaking. Please look at your book for better pictures. And do be ready to graph sine and cosine on the test, okay? It's an easy way to get some points. It's also an easy way to lose a bunch of points if you don't know how. But you can come up with these pictures also from just tracking around carefully on the unit circle. Alright? And then finally, don't forget about the simple sort of applied problems we did last time I think we met. Like you're 2,000 feet away from the base of a tall building, and you observe the angle of inclination to the top of the building is 45 degrees, How tall is that building? That kind of question. So, do try to be ready for that. Thanks, guys. I better stop here.